All right, looks like we've got a good amount here in the room, so we'll go ahead and get started. Good afternoon, everyone, and welcome to today's EOL seminar. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Wei-Yu Chang. Dr. Chang received his bachelor's degree from the Department of Atmospheric Sciences at Chinese Culture University in 2000. He then went on to obtain his master's and PhD from the Graduate Institute of Atmospheric Physics at National Central University, where he now serves as assistant professor. Dr. Chang is no stranger to EOL, having been awarded an ASP postdoctoral fellowship and continuing research ties with several EOL scientists throughout recent years. He is currently visiting our own Dr. Wen-Chao Lee. Dr. Chang's research expertise encompasses radar and mesoscale meteorology, cloud physics, numerical model validation using dual polarimetric radar, atmospheric variable retrieval, and observation error covariance analysis. His recent publications span from characterizing uncertainty in raindrop size distributions with collocated instrumentation to estimating precipitation during the epic Colorado flood event of 2013, to snow density retrievals from collocated measurements during the Ice Pop campaign. Please join me in welcoming Dr. Chang for his seminar titled Retrieving the Liquid Water Content and Characteristic Drop Size of Rain Using Collocated X and K-band Radars. Dr. Chang, welcome.
Thank you, Sarah. Can everybody hear me well? Good? Okay, good. So I'm Wei-Yu Chang. I'm very happy to be back here. After the pandemic, it's been a long time. So I see lots of new faces and old faces, so that's good. I'm from Taiwan, in case some people who don't know me. I'm from National Central University. My title today is shown here, and this picture is a mobile radar operated by our team. So our team, we have 3 professors. I'm on the upper right. So I'm working on mostly on radar data quality, polarimetric radar, microphysics retrievals, radar QP, and also I do some mesoscale meteorology analysis. So the other 2 team members, Professor Liao on the left, mostly working on the data simulation. He works on the 3D bar and the 4D bar. The 4D bar is a V-dress, and he has a very good close collaboration with Dr. Jenny Sang. And he's also very good in terms of the 3D wind retrieval and further to the 3D thermodynamic retrieval. He has tons of paper about the retrieval technique. And lower right is another colleague. His expertise is also data simulation, but focusing on the LEDCAF. With the LEDCAF, it's very easy. They can assimilate all different kinds of the data. So recently, he working on the moisture assimilation, try to assimilate MPD data, and also they assimilate the reflectivity data. And he's working on the polarimetric radar data assimilation right now. He also working on the nowcasting using Maple system, and he also working on the microphysics scheme, try to modify the single moment scheme to the double moment scheme. So we are a team. So you can see that each of one of us has different expertise, but we are all surrounded in the center of the radars. So we use the radar data a lot. We have a long history about radar meteorology back to a long time ago. So I just cut short the history a little bit. So we have our first C-band polarimetric radar from 2004 December. So that's the first polarimetric radar in Taiwan. And then later we have a mobile radar TEAM-R on the upper right. It's an X-band radar from 2008. So the radar actually participated in a very important field campaign in Taiwan. It's a joint field campaign, SOMAX TEAM-REX. S-POL was also participated in that experiment as well. And so the team is central by, we have working on the radar data a lot. So not only the SOMAX TEAM-REX, after that we TEAM-R participated in Ice Pop, which is in Korea, 2017. So that's why we're working a little bit about the snow observation data analysis. We also participated in TAHOPE, which is a field campaign in the Taipei city, mainly focusing on the severe thunderstorm. And then the ESR 2020 and 21, mainly focusing on the winter frontal system in northeastern Taiwan. Then is the TAHOPE Precip 2022, focusing on the Wei-Yu front and south and the torrential rainfall. So as you can see that for the past decades, I would say, the team working on the Wei-Yu southwestern monsoon, thunderstorm, and winter front precipitation. So by using the simulation, numerical simulation, data simulation, and all different kind of analysis technique developed by our team, we try to understand the precipitation process. So recently we want to do something a little bit new or extend or explore some different topic. So next we would like to work on the cloud and also marine precipitation a little bit. So the reason why we can do that is because Center Weather Administration is the weather service in Taiwan. It's going to acquire a dual wavelength XKA band beam match radar next year, June. So the radar can perform very high sensitivity and with a matched measurement from X band and the Ka band. So this opened a new door for us to study the cloud. Before the cloud, this radar, we cannot do the cloud observation. We can only limit on the precipitation study. So with this radar, we will be able to explore more cloud characteristic in Taiwan. Another very important thing is the shipborne radar. So this is a picture of our new Ocean Researcher 1 RV. So the radar will be ready by next year, 2025, April. So it will be an EEC shipborne parametric radar C-band. So this research vessel will contains all different kinds of instruments from the sounding, salammeter, air quality box, micro radar, and also other oceanography instrument under the water and also near the surface. The whole idea is try to encourage the collaboration between two research areas and to explore the marine meteorology and oceanography. So we already tried to do that in early this year, that we have a voyage from Taiwan to Palau. It's a round trip voyage. So we put the MRR on the research vessel. So we are able to collect several precision events. So with this new instrument next year, we are able to understand the microphasic process of not just the rain, but also the cloud. So that will help us improve the QPE and the QPF. And also that will help us to improve our capability to observe the extend observation on the land to the ocean. So which we used to lacking observation of the marine precipitation system. So for these two systems, we need to be ready and prepare some corresponding technique. So for example, the calibration, quality control for the cloud radar, or for the shipborne radar, one thing very important is the ship motion compensation correction. So these two technical study have been done right now. So another very important thing is when the radar scanning, assuming that location, and we actually can only scan like 180 degrees. On the back is blocked by the bridge. So we cannot really do fully scanning. So in order to improve the capability of the shipborne radar, we are thinking about wanting to do the vertical observation as well. So in order to get the vertical observation, which is the vertical profile of the content or range of size information, the parametric radar cannot provide such information in the vertical direction. So we need to rely on dual wavelength technique. So along with the cloud radar, it seems to collocate dual wavelength techniques quite important for us that will open a new door to retrieve the cloud property. So that's the reason why I would like to share the result we have been working recently. So basically retrieving the liquid water content and the characteristic drop size of rain using Collocated measurement. And in this case, because these two instruments is not ready yet, so we propose to use the X-band radar and the K-band radar. So the X-band radar is the figure on the right here. You can see it's TEAM-R. So it's a mobile radar, so we can have a vertical pointing very regularly. And the MRR is essentially just a vertical pointing radar. It's a K-band. So during the TAHOPE 2022, we have collocated two instruments and have every 12 minutes, we'll have a collocated vertical pointing measurement for the whole experiment. So we would like to use this data set to help us to develop the dual wavelength technique. And this technique in the future can be applied to the cloud radar and the shipborne radar. So today I would like to introduce the methodology. So basically we we're focusing on the liquid water content retrieval. The technique itself is based on Alice and Vivic 2011. And we further extend the technique to a ZPHI method I'll introduce later. Another very important thing is the misscattering correction, which has been considered, but we try to correct the misscattering effect. And once we develop the methodology, we want to check our result. So we want to do more idealized OSSE study, and then we will do real case study, and then the summary. So what is the dual-wavelength retrieval technique? So polarimetry radar is not sensitive to the cloud because when the cloud, if the size of the cloud drop, usually it's very, very small. So when they are very small and it's spherical, so the cloud radar doesn't work very well. So the polarimetry radar doesn't work very well because they are all spherical. The ZDR doesn't work. So, and also the precision radar doesn't have a good sensitivity. And also, if you have a drizzle in the cloud, and one single big drizzle will contaminate your measurement and jeopardize your liquid water content retrieval using reflectivity. So the dual-wavelength technique become very important. And dual-wavelength technique is not new, it's very old technique. You can see from 1970, it has been showing some research results from using the dual-length radar measurement. So the first important application is the reflectivity correction, and the second is to be the liquid water content retrieval. So the reason why we can do liquid water content retrieval is because the moment of the liquid water content is very close to the attenuation, specific attenuation. So we can do liquid water content retrieval very well. So the attenuation itself is basically the extinction and the scattering of the EM wave. And the specific attenuation it's controlled by three different things. First one is your dropsize distribution of cloud or rain, and then the temperature, environment temperature, and the wavelength of the radar. So once you know the temperature and the wavelength of radar, you're supposed to be able to use attenuation to retrieve the liquid water content. So the equation looks like this, a very simple power-law relationship. So the idea here is try to get a good attenuation and then estimate the liquid water content. So how do we do that? So we have two radar. So you can see this is example that if we have two radar co-locate the same measurement, one's longer wavelength, the other one is shorter wavelength, because we want to derive the attenuation. So the idea is use the DWR, dual wavelength ratio technique. So this is the example that if we have two measurement from long and short wavelength radars, then we can get this monotonic increased attenuation, which is DWR as well. So this can give us some idea about how's the attenuation along the radar beam. So if you have a very flat DWR, that means you have a weak and low liquid water content. And if you have very steep DWR, that means over there you have a strong attenuation and you have high liquid water content. So the idea is very simple. However, in reality, you have to consider all other different factors can affect the measurement. So the radar can have their own measurement noise, and the wavelengths may have some different degree of the misscattering effect. And you also can have a gas attenuation, and you might have the mismatching and sampling volume from two different radar, all different kinds of error source from the reflectivity. So it makes the gate-to-gate comparison to derive the coefficient, the attenuation become very, very difficult. So this is just a very simple example that if you have noise in the Z, long and short wavelength radar, then your DWR will be no longer monatomic or increase, then you have up and down. So once you have up and down, you cannot really calculate the slope of the DWR. So that would make gate-to-gate calculation very challenging. So the study here is we want to develop the DWR process procedures for dual-wavelength radar system. In this particular case, it's the TEAM-R and the MRR-PRO. And the second is we want to evaluate the performance of the specific attenuation retrieval method. Basic is the fit from Alice and Vivic 2011. And we want to propose a slightly different algorithm, which is ZPHI-based algorithm. So first, I would like to introduce the algorithm from Alice and Vivic 2011. So it's a fit-based liquid water content retrieval algorithm. So the idea is very easy. Once you have Z, and with the coefficient A and B, then you can calculate your attenuation. Then the question is, how do we get the coefficient A and the B with the DSD variability and also the environment temperature change. So the idea is once you have a dual wavelength measurement, long and short wavelengths, and you can calculate your differences of reflectivity, the DWR, from the close radar gate to the farthest radar gate. So the total attenuation, if you calculate the mean, will be the mean attenuation. And you also can get your mean reflectivity from longer wavelength radar measurement, which assuming there's no attenuation. So in that case, each beam, you can get a mean value of Z and the mean value of attenuation. Then with several beams, you have different, you can fit this line. And in this, the slope here will be actually the coefficient B in the ZA relationship. So that's the procedure to get the B coefficient. Then once you get the B, then you can apply to each beam. So remember here, it requires several beams because each dot represents one beam. So you need several beams to get the coefficient B. Once you get the coefficient B, then you can get coefficient A from each beam. Then because you just essentially apply the B value and then you just calculate the A value. So each beam will get the different A value. So once you get the A and the B, because the B is a fixed value and A is the beam dependent. So in order to, then you can calculate your attenuation at each range gate. Okay, so in order to do that, there's some assumption. First, you need to have an attenuation, an attenuity, the ZL. That means that you need to have a long wavelength. You have a measurement of reflectivity from longer wavelengths, which has very little or nearly none attenuation. Then once you have that and follow the procedure, you will get a fixed B and the beam-dependent coefficient A. So the advantage of this algorithm is because it seems the procedures have lots of averaging. So you will have very uniform A attenuation, and you avoid to use the noisy DWR because you only need the total pass of the attenuation. You only need the total pass of attenuation that basically is like this. You just need the PIA, the pass integrate attenuation. So you avoid to use the gate-to-gate DWR. But the downside of this approach is you lack the flexibility of coefficient A. You only have a beam dependent. And sometimes the beam doesn't have enough data, you are forced to use, collect the data from several beams in order to get one coefficient A. But we all know that coefficient A should be gate dependent because the DSD is very different. But anyway, once you get coefficient A, you will be able to use the coefficient A to derive your liquid water content and radar estimate size and mass weighted diameter. The mathematics just here, so it's not very complicated. But remember, this coefficient is temperature dependent because attenuation can be very different from different temperature. So simply just you can collect local Disdrometer data and then you can calculate the coefficient accordingly. So in this case, we have 11 years of Disdrometer data, so we can calculate coefficient A and B or all the necessary coefficient in order to retrieve the liquid water content, mass weighted diameter, or radar estimate size. So the second algorithm I would like to propose here is called ZPHI retrieval. So this retrieval technique has been used by satellite people a lot. And recently, the algorithm has been applied to the QPE by Rusco 2014. So the idea of the PIA, a ZPHI algorithm, is the attenuation at each range gate R can be calculated like this. And this equation looks very scary, but it's actually very simple. ZA prime represents the measurement of the reflectivity at each gate. You don't need to do any attenuation correction, just attenuated, measured the reflectivity. And the B is a fixed value, and this value has been shown theoretically has very small variability. So this should be easy to get. And the rest will be here. So if you take those equations, it's quite similar to previous one. We also try to get A by something Z-B relationship. But the difference is here is this part is not a fixed value anymore. It can change. So we can change that, but how? So this equation is basically also, this is just the I function, and you can apply I function R1, R2, and R2. So basically you use the whole path of the radar measurement, then you can get your I function. So in this equation, everything can be simply derived from the measurement itself. So it becomes very easy and more can better capture the DSD variability. Therefore, your attenuation at each range gate can perform better. However, this technique do require the total path attenuation. So the conventional approach of this idea is try to use the VDP, which is a parametric radar measurement. So once you have an increment of VDP with the coefficient alpha, then you can get the path integrate attenuation. However, we all know the alpha value is also has very high variability. Even though you have the same increment of VDP from R1 to R2, you still can have very different PIA. However, because we are using the dual-wavelength technique, we no longer need to use this equation. We can simply just replace the PIA from two radar measurement, which is the total path integrate attenuation. So we can replace this one by using the dual-wavelength measurement. So the advantage of this technique is once we have PIA from dual-wavelength measurement, we can simply put this back to this equation. And then we can have a gate-dependent coefficient A. Unlike the previous fit algorithm, the A is really tied on the data you choose. You need to do lots of fitting. Then we can have a liquid water content, mass weight diameter, and the radar estimate size from gate-dependent A attenuation here. So this is supposedly this algorithm should perform better. But another thing we need to think about is the mean-squaring correction, because once you choose a shorter wavelength radar, then you might get the mean-squaring effect very easily. So in this case, because we are using K-band, this is the single particle simulation from 1 to 8 millimeter. So blue is X, red is K-band. So you can see that between 1.24 and 3.11 millimeter, the K-band reflectivity actually higher than X-band reflectivity. So that will cause an issue because we try to calculate differences from these two radar, and we're assuming the X-band will have less attenuation. So we're assuming that the X-band measurement of reflectivity will always higher than K-band, so we can use the differences to derive attenuation of K-band. However, with the mean-squaring effect, the K-band actually will give you higher reflectivity than X-band. Then you cannot get attenuation, or it's mixed together. It's very hard to separate. So we want to evaluate how serious of that scenario because we have lots of range up between 1.24 and 3.11 millimeter. So on the right here is the simulation of the differential reflectivity between X-band and K-band. So you can see here, anything below 0 dB means your K-band measurement actually is higher than X-band measurement. So this simulation has not considered the attenuation effect yet, simply just the pure reflectivity simulation. So now this is purely caused by the resonance effect or mean-squaring effect. So that will cause a big problem because you can see that lots of data is below 0. And if we take a look at the size, because we want to retrieve the liquid water content, so between 1.24 and 3.11 the equilibrium diameter, you can see we have lots of range drop over here. So the red line is the D⁻³ weighted distribution. So we can see, you might argue that we have a lot of small range drop, but in order to get the liquid water content, we still heavily biased by the mean-squaring effect. So in this study, we try to use a very simple way to correct the mean-squaring effect. On the left is the DWR, and the X is the reflectivity from X-band, because X-band has less attenuation effect, so we can use that as a reference. So you can see that with the increase of the reflectivity, we can start to see the DWR become negative. So you can call this a mean-squaring bias. So that means mean-squaring will give you underestimation of DWR. So you can see the gradual increase between 20 dB and 55 dB. And you can see that most differences are between 25 to 45 dB. So you can imagine that if you have an X-band measurement from reflectivity, and if it's 25 to 45 dB, that means when you try to compare the K-band, you will have mean-squaring effect. So the correction is very simple. We just get this mean line, the red line, given reflectivity, then we just simply apply the very simple fitting curve. So we just use this fitting curve and see how that can help us remove the miscarrying contamination. So on the right is after we apply the miscirculation, now the error is close to 0. That means we minimize or mitigate the miscarrying effect. Okay, so how exactly miscarrying effect will affect the things we try to do, the dual-wavelength retrieval technique? So this is the 4 different examples. First one, what happens if you have a scenario like upper left? So if you have upper left, that means you have weak reflectivity, but you start to have strong reflectivity in the far side of the radar measurement. You found that your X-band measurement, which is the blue line, and actually lower than the red line, which is a K-band measurement. This is purely because the miscarrying effect. So if you just use the raw data to calculate your DWR, you will have negative value, which is unrealistic. So in this case, you will underestimate your total path integral attenuation. With the correction we propose, we will subtract the miscarrying effect. So the red line will become the red dashed line. Now the K-band measurement is lower than X-band due to the attenuation. Now we can have a more reasonable PIA, which is a dashed line here. So then we can reasonably derive we can use the smoothing technique to get this black dashed line. So we can correct the miscarrying effect. So this is underestimation of PIA scenario. On the other hand, if it's the lower left, it's opposite scenario that closer radar have stronger reflectivity, but away the radar is weaker reflectivity. You actually overestimate your PIA because the miscarrying effect would lower your DWR. Therefore, the total PIA will have higher values, like the blue line, yellow line here. So once we correct that, we can have this yellow dashed line. And also the black dashed line is more realistic because everything supposed to be positive value rather than we have a negative value. So that is another scenario how the miscarrying effect would jeopardize your PIA calculation from dual-wavelength technique. So, but the miscarrying is not always there. So this will have 2 different scenarios that if your measurement is contaminated all the way by the miscarrying effect, then it becomes like a bias. So your PIA is just a bias value. It doesn't affect your total value. So it doesn't affect your PIA calculation. Or you only have in the miscarrying contamination in the middle of the beam. It also doesn't affect your total PIA calculation because essentially you just need the data closer radar and the data away from radar. So you just need the total PIA. So this is just an example showing if we apply if we apply the correction, we can remove those underestimation very well, and everything become positive because we don't want to have negative value with DWR. So once we consider all the new algorithm and the miscarrying effect, we want to check if we want to, if we apply the dual-wavelength technique, how these different things will affect our retrieval result. So we have a very complicated OSSE study. So first one, we want to check different kind of attenuation we can derive. So the first one is assuming we can derive perfect attenuation. Basically, we have a K-band true reflectivity and subtract K-band attenuated reflectivity. So we can get perfect attenuation from K-band. And the second one is assuming we have X-band, which is considered as a TEAM-R, but TEAM-R can have attenuation. But assuming there's no attenuation, then the differences between 2 is attenuation of K-band and the miscarrying effect. So remember that 2 different waves, they still have miscarrying effect. Then if we put more realistic X-band measurement, which we consider the X-band attenuation, then the difference between these 2 measurements would be K-band attenuation, miscarrying effect, and the X-band attenuation. But we can do some correction about the X-band attenuation using some simple technique. Basic the ZPHI technique, but different ZPHI, but simple one ZPHI. So we can apply the ZPHI technique to correct the X-band measurement. So now we have K-band attenuation, miscarrying effect, but we have an X-band correction error because all of the correction remains some error. And the last one is if we consider miscarrying correction. So this one will be the closest realistic scenario, this is what we are going to face in the real observation data. When we try to compare or derive the PIA from two wavelengths radar X-band and K-band, the differences should be considered three different components. First one is the attenuation itself from K-band, your miscellaneous correction error, and the X-band attenuation correction error. So we want to compare this one and see, and most important thing, we want to see if we can, once we apply the attenuation correction and correction, can we gradually get better result? And this test is only based on the Z-fit retrieval method. So this is we want to just check the attenuation itself. So this is the attenuation, specific attenuation, dB by kilometer. So this is pure Disdrometer simulation. So this is the most theoretical, most ideal scenario. And lower right is the closer to reality. We have a correction and X-band attenuation correction. So the figure itself is too complicated, but you can take the bar on the right. So you can see that we calculate root mean square error, mean absolute percent error, and the correlation coefficient. So if you check the first one, of course, the ideal scenario is always the lowest error. And the right is the closest, the realistic scenario have slightly higher error. But most important thing is we can make sure the error gradually decreases once we apply the attenuation correction for X-band and the mean correction for K-band. So we make sure the error can drop as we expected, both the root mean square error and the mean absolute percent error. So now we want to apply to the technique and compare ZPHI method and the fit method. And this is for the OSSE study, we want to have a more closer to the scenario, the reality. So a little bit different is we have about 30,000 Disdrometer data, and we can do all the TEAM-R simulation, get the reflectivity, attenuation, everything, then we can simulate attenuated X-band and K-band measurement. But a little bit difference is when we arrange those data, we try to use TEAM-R measurement as a reference. So we can create very similar profile compared to TEAM-R, closer to what happened in the reality. Then we can use the profile to help us to test algorithm. Because the OSSE data, because everything is from Disdrometer data, so we can get out the true value of liquid water content, radar estimate size, we can compare them and make sure our retrieval algorithm is good. So we can compare the truths and our estimation from the dual-wavelength technique. So lower here is the X-band attenuation, attenuated reflectivity, and K-band attenuated reflectivity. I just let you know that it looks like the real data. And the bottom right is the DWR, basic difference from two. And you can also notice that you can see some negative value, which is unrealistic. So this is because the miscarrying effect. So we are going to check everything. We want to make sure we create as realistic possible data and then test the algorithm. So this is the result. And when basically we compare two different things. First, we want to compare the fit algorithm and the ZPHI algorithm. And we want to compare with the mean correction without the mean effect correction and with the mean effect correction. So this case is the liquid water content. So this is the truth because it's the OSSE, so we have the truth. So this is from the fit algorithm, and this is from the ZPHI algorithm. So we can notice that for the fit algorithm, because the design of the algorithm itself smooths a lot of the data. So you can see more smooth retrieval from fit algorithm. On the other hand, the ZPHI algorithm allowed to contain the DSD variability and better capture the DSD variability. So the retrieval result is not that uniform compared to fit algorithm. And you also see both of them are very, if you look not very carefully, like loosely, you can see it's quite similar to the truth. But truth, there are lots of noise, but you can see they are quite close. So because it's an OSSE, so we can test. Idealizedly. So you can see that this is the comparison. X is the truth, and Y is the retrieval. And you can see that for the root mean square error, you can see the ZPHI algorithm is always better than the fit algorithm. And also with the mean correction, we can have the lowest error in terms of liquid water content. And then this is the radar estimate size. Basically give us similar result. The fit has very, very smooth IS, and ZPHI give more texture. And this the truth is closer to the truth. In terms of root mean square error, you also can see that the ZPHI method is showing lower error compared to fit algorithm, and with the mean correction and ZPHI algorithm give us the lowest error and best performance retrieval result for the IES. And last one is the mass weighted diameter, basically the same, but slightly differences is we found that in Dm, it turns out the fit with mean correction give us the lowest error, but the ZPHI also have very comparable rate error, but it's not the lowest one. But anyway, but you can see that. Sorry. So you can see that the mean correction does have very big impact in terms of the dual-wavelength retrieval technique. Okay. So now to switch to the real case. I probably need to go fast. So the real case is the TAHOPE 2022, and it's IOP-3. We have a menu from past northern Taiwan, and that's a perfect case to examine the algorithm. So, and the two collocated radar, TEAM-R and MRR-PRO, we try to match the measurement as possible. The radio resolution both have the 50 meters, and the beam width will be different, and they have different time resolution. So you can see on the top is a TEAM-R has 12.5 minutes time resolution. So this is the time, and Y is the vertical direction. And MRR-PRO is consistently vertical pointing, so it's a 30-second measurement, so you can see higher temporal resolution. But doesn't matter because we only want to use the collocated measurement to retrieve for the retrieval. Sorry. And then to apply the data to the retrieval, we need to do lots of data quality procedures. So we have the two parts. First part, the basic QC. So basic QC means we apply the system bias correction to the TEAM-R and also gas attenuation correction. And for the MRR, we apply to the very standard QC procedure proposed by some researcher of 2022. There's an open software called Euro, so we can do basic QC. The gas attenuation here, we basically use the ground surface measurement station very close to the TEAM-R, and we're assuming that the temperature decrease in a more adiabatic rate, depth rate. But this is just very simple way to test. We have to do more studies, see how reasonable that is. But anyway, this is our gas attenuation correction. For the total pass to 4.25 kilometer, in this case it's 2.7 dB DWR differences from two radar. Then we will do more fancy correction. We found that two systems have some issue in terms of the vertical, there's some shift of the data. So, and then we use the bright band, which is the folding of the raindrop, and to check how consistency of the data from two measurements. Turns out there's slightly differences. So we correct that. We use the melting layer to help us to correct the data. The vertical resolution, we kind of rearrange, interpret the data a little bit. So we kind of move so once we do the correction, the melting layer height will be more consistent. Another thing would be the TEAM-R X-band radar need to do attenuation correction, and the K-band MRR-PRO data need to do mid-scale correction. So, and also we also do the time lag correction because two measurement doesn't really synchronize very well. So sometimes we need to shift the time a little bit. So we also do the time lag correction in order to improve the consistency of two measurements. So we will have basic QC and we have advanced QC. So once we apply the data and get a retrieval, and then the problem will be how do you validate? How do you know it's correct? So what we do is we use the S-POL data. So S-POL is somewhere here in Hsinchu. TEAM-R is here. So S-POL has consistent RHI scan every 12 minutes. So we can use those RHI scan on top of TEAM-R and the MRR-PRO, so we can compare the retrieval. So from the ZDR and the ZH measurement from S-POL, we apply a DSD retrieval technique to derive the Dm and NW. So once we have these two values, we can calculate liquid content, IES, and everything. Then we can do the comparison. But keep in mind, the retrieval technique is very simple, so maybe there's some error. But anyway, so this is the retrieval result from our dual-wavelength technique. So this is just an example that you know that this is I think this is 1 day time series of liquid content and IES. So now we want to see the consistency between our dual-wavelength retrieval technique and S-POL retrieval. So this is just some comparison. If we have a basic QC and advanced QC, you can see once we have advanced QC, both FIT and the ZPHI algorithm can give us more reasonable PIA value, because the PI value is supposed to be increased with the height. And also, they should be narrow, not very spread. If it is too spread, that means the data itself is too noisy. So we found out once we apply more complicated QC procedures, the data itself will become clean and better. And the most important thing is we want to compare with S-POL. So compared to S-POL, it's very challenging to do gate-to-gate, point-to-point comparison. So before we jump in that, we want to do very rough comparison. So on the left-hand side is the retrieval from S-POL. Basic just liquid water content and the Z, this is just the PDF. And this is similar, but the IES with a Z as a PDF. So X is the liquid water content and IES, and Y is the reflectivity. So ideally, if our retrieval is reasonable, we should have similar pattern. So on the right, these four figures are the retrieval from different dual-wavelength technique. So this is the FIT, and I think these two columns is the FIT algorithm. On the right is the ZPHI algorithm. But the lower one with the, let me see, lower one with the, okay, I think on the up, it's okay. The second column is the FIT algorithm. On the right, third column is the ZPHI algorithm. And the lower one has the mid-scattering correction. So theoretically, this one should be better. So how we evaluate that is we try to compare the overlap of these two, our retrieval with S-POL data. So the overlapping area is shown here by percentage. So you can see, in general, the FIT algorithm is showing lower percentage. That means the consistency is lower. On the other hand, the ZPHI algorithm gives you more consistency, higher percentage. That means more coverage. That means they're more overlapping. And lower right with the mid correction can further improve, give you higher value overlapping. So that gives us confidence that the ZPHI is better and the mid correction is important. And if we apply, oh, sorry. So if we apply the, wait. So, wait. Okay, this is just the basic QC, sorry. This is the advanced QC with the mid correction. Now we can see the overlapping areas increased to 47% for the ZPHI method. Oh, sorry, this is liquid water content and IES. Okay, so this is the two different parameters. So overall, we want to compare. If we just do the basic QC, the ZPHI method showing higher coverage percentage if we take this red bar. And if we do advanced QC, we also get the ZPHI is the best. So overall, the ZPHI with advanced QC will give us the better coverage compared to the S-POL retrieval. So now we try to do, can we do more detailed comparison by separating the convection and the striatum region. So we take the data, we select two periods of time. One is the convection period, one is striatum period. So this is the convection period. So this is the vertical velocity from TEAM-R. You can see some vertical updraft here. So reflectivity looks very convective. The other time period is striatum. So you can see, so yeah, this is striatum. You can see very pronounced bright band signature and weaker, the vertical velocity doesn't show that much rigorous activities. So we select these two periods to see our retrieval technique, whether they are similar to S-POL result. So by comparison, we do something slightly different because when we retrieve the liquid water content and the mass weighted diameter, we want to know the mean characteristic of convection and striatum region. So the left-hand side figure is the retrieval from convective and the striatum region. So for the convective region, blue dots represent from ZPHI, and the red dots represent the S-POL retrieval. So we can see that in terms of liquid water content, our dual-wavelength retrieval is slightly lower compared to S-POL in terms of the liquid water content. But for the Dm, they are quite similar in the convection region. But the striatum region, which is the light blue and the yellow, you can see that they have similar liquid water content, but the S-POL showing higher Dm compared to dual-wavelength retrieval. So this is kind of like something we don't like because we start to see some bias in the retrieval technique. So on the right is just basically just a similar figure, so I just skip that. Another thing we want to know is how about the vertical gradient of these two retrieval, because we all want to know that if the liquid water content is downward increase or decrease, because that would represent different microphysics characteristics, and also the Dm, whether it's downward increase or downward decrease, that represent whether it's a breakup of process, evaporation process, or collision coalescence process. So in order to do that, because the TEAM-R is 20 kilometers away from S-POL and there's some ground contact contamination, so we can only use the data above 1.2 kilometers. And we don't want to use data contaminated by the bright band, so we only can use the data below 4.2 kilometers. So basically, we just calculate the gradient between this area and this area, basically just top subtract the bottom. So that means positive value, that means downward decrease. Positive value downward increase. Wait. Positive value means downward decrease. If the negative value means downward increase. So this is quite, I'm sure everybody see this figure. It's very complicated. I think the right-hand side is better. So that we take a look at the convection region, the blue triangle, and from ZPHI and the S-POL, red triangle. So it seems like they all suggest that the Dm is increasing downward, but not the liquid water content. For the stratiform region, they have more consistent result, which is the blue dots from ZPHI and the red dots from S-POL. They're showing more similar result. So we start to see some inconsistency, but also some consistency. So in summary, that from the OSSE, we found that the ZPHI-based dual-wavelength method can show more realistic liquid water content and the Dm relationship in OSSE in a real case. And we found that the mid-scattering correction can improve the attenuation estimation and the liquid water content and Dm retrievals. However, in the real case that when we compare to S-POL retrieval, we found that our dual-wavelength technique tend to underestimate liquid water content in the convection region and also the Dm in the stratiform region. In the convective precipitation, Dm tend to increase during sedimentation for both S-POL and the dual-wavelength retrieval. However, in the convection region, liquid water content tend to increase from dual-wavelength retrieval and S-POL showing otherwise. So, but this inconsistency gives us a very mixed feeling about the performance of the algorithm, because in the OSSE we see very positive signal that the new technique, the new retrieval algorithm is supposed to perform better. But remember that when we try to compare with the S-POL, there are so many reasons can jeopardize the comparison, because remember that there's always an instrument error, and the sampling difference of these two instruments is really huge. And the retrieval technique we use for S-POL to retrieve the DMNW is very rough. We haven't really fine-tuned the retrieval. So in overall, that we still have positive feeling about the entire study that the ZPHI mass dual-wavelength technique should be work pretty well. And in the future, we want to further improve this technique, and we want to apply this technique to in the future CWA dual-wavelength cloud radar and also the RV NOR1 C-band radars. Thank you.
Thanks for that interesting seminar. For those online, quick reminder, Slido screen is at the bottom below your video screen. Please enter your questions online. We do have one question online already from Vivek. He says, good presentation. How did you range ground-based Disdrometer Dropsize distribution measurements as a function of range for the OSSE?
Thanks for the questions. So how we do is we have 3,000 Disdrometer data. So we can get the DSD for each range gate. So how we arrange the data is for the realistic case, we have a TEAM-R measurement. So let's say if we have a TEAM-R measurement reflectivity 30 dB, we just randomly choose one of the DSD which has minus plus 0.5 dB of 30 dB. So we can just select one of them and use that as that particular gate. So that means if we have a profile from certain reflectivity value from the bottom to the top, we would choose the closest reflectivity for each gate. So that and that DSD we're assuming the range resolution is 50 meters, which is in our case is 50 meters. So we want to create as realistic as possible DSD. So we want to use that to create the OSSE data.
Great, thanks for the question, Vivek. Are there any questions in the room?
So correcting for me-scattering is pretty difficult, right? How confident are you in that? Because there's a lot of ambiguity. In fact, how do you really know that that's working?
Well, in practice, I don't know because we don't have any reference truths. So this is just, as you can see that I cannot perfectly correct the me-scattering effect. So by looking at this figure, I only can reduce the me-scattering effect. So that's why I kind of emphasize that in the OSSE that the most realistic scenario, which is the lower one here, so still there's a me-scattering correction error. So I admit that I only can reduce the me-scattering effect and its impact in the PIA and the dual-wavelength technique. But I don't think I can purely remove it. Yeah.
Sorry, I'm going to hit on the me-scattering again. So if I heard correctly, between the X-band and Ka band, you detect or you assign the me-scattering when the Ka band reflectivity is higher than the X band. Is that correct?
Actually, no. We don't assume any scenario. So by simulation study, we already know that the me-scattering effect will happen if the reflectivity from X band is greater than 20 dB all the way. And you can see the red line is the mean. So majority of them give you a higher K-band value until like around 50 dB. So in practice, when we apply this equation, as long as the K-band measurement is meet one of the four equations, actually two, because the other two is 0. So once they fall into that range, we will apply the equation and get the correction, we just correct the value. Yeah.
My second question is, in this process, have you used S-POL data, or S-POL data is only used for validation purposes?
We did compare the reflectivity purely. I didn't put it here, but we found it's very noisy. But here, that's actually we are working on that part. So in our data processing, we actually smooth out a lot of the data. So here, so we have a procedure to smooth the MRR data, and also we smooth the S-POL data because S-POL is RHI on top TEAM-R and MRR-PRO, and it's 20 kilometers away. So S-POL resolution volume is huge. So TEAM-R has a 360-degree rotating for when we do vertical pointing. So we actually try a different way. We think instead of averaging the data, we try to look at the comparison using more like ensemble comparison. So what we do is we treat those 360-degree azimuth being as single vertical pointing profile, so we can see the spread. And we found that most of the time, the reflectivity itself is very different from S-POL RHI measurement. So that means we might have lots of issue in terms of the sampling differences between S-POL RHI and then TEAM-R vertical pointing. So because they are not perfectly aligned, because RHI from S-POL might scan maybe 30 seconds earlier, and we do vertical pointing 30 seconds later. So that's the time differences. And so we also try to see if we only select those data, it's very close, and that does improve our comparison. But that limits the comparison size, data size. So we're still struggling how to do comparison. So that's why I say that even though when we try to compare with S-POL, the result doesn't look very promising. But I think most of the time it's not because the algorithm itself, it's because the sampling issue play a big role there. Yeah. And also the retrieval technique is not perfect from S-POL retrieval. We are using very simple retrieval technique.
Yeah, I was about to suggest that assume S-POL has no attenuation, ground truth. Then based on the vertical RHI vertical profile, that may provide you some references on the attenuation by the C band or Ka band. But if you have sampling issues deviate by 10 minutes, then that may not be a
and
good
also
way to do it.
the alignment may not be perfect in spatial. So
Any other questions in the room? All right, I don't see any in line, so I have a question. As an airborne observationalist, have you thought about perhaps comparing your retrieval with airborne observations of the Dropsize distributions?
I think that's doable because I talked to Vivek, but he's recently working on the W-band and LiDAR. But he used to do W-band and K-band maybe, I don't know. S-POL has a dual-wavelength measurement before, but not now. But I think it's worthwhile to try. But I know hypercloud, I think you guys are thinking about put the K-band for the airborne radar, right? Now it's only W-band. So maybe in the future you have KN and W, we can do cloud water content retrieval. Yeah.
Thanks. Any other pressing questions? If not, let's thank Dr. Chang one more time. He's in town until Friday if you come up with other questions.
Thank you.